Section 2. Intermolecular forces in solids, liquids, and gases. Chem Talk. Intermolecular forces versus kinetic molecular motion. Characteristics of solids, liquids, and gases. In solids, the particles, atoms or molecules, are not able to move around much because they have a fairly strong attraction for one another. These intermolecular forces are electrical in nature, meaning they are related to the number and position of electrons. Particle motion of solids consists only of vibrating in place, giving solids a definite volume and shape. Solids can be heated until the vibrations become so severe that the particles begin to break free from their place in the structure and become liquid. This added heat energy becomes kinetic energy and overcomes some of the intermolecular forces of attraction. In the liquid phase, the particles are still attracted to each other and are still in contact with each other. However, they are not locked into a fixed place by the attractive forces. The liquid particles are free to move past each other as well as vibrate. Liquids have a definite volume, but not a definite shape. A liquid can be heated until the kinetic energy of its particles overcomes the remaining forces of attraction and the substance becomes a gas. Gases are different from liquids and solids because there are relatively large distances between the particles, atoms or molecules. This makes gases compressible, whereas the compressibility of liquids and solids is negligible. A gas is characterized as being composed of fast-moving particles in constant random motion. Gases have neither definite shape nor definite volume. The intermolecular forces of attraction have not been changed by these phase changes. The process of going from solid to liquid to gas by adding heat energy can be reversed by cooling. By removing heat energy, a gas will become a liquid and a liquid will become a solid. This happens because the particles are slowed enough that the still present intermolecular forces of attraction exert their effect. Intermolecular forces of attraction and nonpolar molecules. Nonpolar molecules, such as the halogens, oxygen, nitrogen, carbon dioxide, and the CX4 molecules, have shapes and bonds that are symmetrical. The electrons of these molecules are distributed evenly in such a way that there are no permanent electrical charges anywhere on the molecules, and the intermolecular forces are small. The symmetrical shapes of nonpolar molecules cause them to have very little attraction to each other. Small nonpolar molecules tend to be gases or liquids with low boiling points. For these same reasons, the noble gases have very small forces between atoms of these elements. As the size of nonpolar molecules increases, the attractive forces between molecules also begin to increase. You saw this for the series of hydrocarbon molecules. Larger molecules have more electrons. When there are more electrons, they may, at one instant, be distributed unevenly. One part of the molecule briefly may have increased number of electrons. This distortion of electrons gives rise to a temporary partial negative charge, represented by the Greek letter delta. Since one part of the molecule has an overabundance of electrons, another part of the molecule must have a deficiency of electrons, creating a partial positive charge. The molecule becomes a temporary dipole, meaning two poles or two charges. This in turn triggers or induces a similar dipole in neighboring molecules, and this process spreads from one molecule to this process spreads from molecule to molecule. These attractive forces, called London dispersion forces, are much weaker than ionic or covalent bonds, which hold atoms together. The polarity causes a greater attraction between two molecules. The molecules are difficult to separate, which is what takes place when a substance boils. The larger molecules tend to have higher boiling points and can be liquids or solids at room temperature. Intermolecular forces of attraction and polar molecules. Other molecules have permanent separated charges as a result of their shape and the types of atoms in the molecule. Some atoms, particularly oxygen, nitrogen, and fluorine, have a greater tendency to pull the electrons of a covalent bond towards themselves. This property is called electronegativity. For example, oxygen is more electronegative than hydrogen, so the electrons in the OH bond are pulled closer to the oxygen atom. This makes a polar bond with a partial negative charge on oxygen and a partial positive charge on the hydrogen atoms. These partial charges are permanent, not fleeting, like the London dispersion forces. Water molecules have two hydrogen atoms attached to a central oxygen atom at an angle of about 108 degrees. Here's the two hydrogen atoms. Here's the one oxygen atom. Here are the angles. The polar bonds and its shape cause water to be a polar molecule. The positive hydrogen atoms are attracted to the negative oxygen atoms of nearby water molecules and form hydrogen bonds. While hydrogen bonds are not real bonds, they are important intermolecular forces. In strength, they stand intermediate between real covalent bonds and the weak London dispersion forces. On a scale of 0 to 100, the relative strengths of these attractive forces are 1 to 5 to 100, with 100 representing a covalent bond. The term van der Waals forces is sometimes used to cover the attractive interactions of both hydrogen bonding and dispersion forces. Many of the unique properties of water are a result of hydrogen bonding. A water molecule has only 3 atoms with a low total mass of 18 AMU. Even so, it has a relatively high freezing point of 0 degrees Celsius and a high boiling point of 100 degrees Celsius. A nonpolar molecule of comparable size, such as methane, CH4, has a boiling point of negative 161 degrees Celsius. Even ammonia, here's ammonia, which also has a hydrogen bonding between molecules, boils at negative 33 degrees Celsius. Water also is unique for its high heat capacity and its ability to dissolve a variety of organic and inorganic compounds. All of these properties make life possible on Earth. When there is a strong attraction between molecules, the substances are probably liquids or solids at room temperature. The alcohols discussed in this investigation have one negative OH group that makes these molecules somewhat polar in nature. Just like water, this polarity increases the amount of heat energy needed to separate the molecules, as seen in the higher boiling points of alcohols compared to the hydrocarbons.